The correlation coefficient helps us evaluate the strength of a linear relationship between two quantitative variables, but it does not do anything else in helping us predict the response variable. To do so, we need to build a model. In this case, a linear model, because the relationship between the time and distance of a driving assignment at Butler deliveries is linear. On a scatter plot, a linear model is geometrically represented by a straight line. In algebra, we learn how to describe a straight line on a pair of axes with the equation y equal mx plus b, where x is the independent variable, y the dependent variable, m the slope, and b the y-intercept. In regression analysis, we do just as much, only we call x the explanatory variable or predictor, and y hat the response or predicted variable. The reason why we use y hat instead of simply y is because we already use the variable y to depict the vertical coordinates for the observations, which on the scatter plot are represented as dots. Also, we call the y-intercept, or simply the intercept, b subindex 0, and the slope b subindex 1. We call it the regression equation, and the model describes the simple linear regression model. It is called simple because it has only one explanatory variable. In the next video, we will learn how to improve the precision of a regression model through the use of multiple explanatory variables. Imagine that you had a couple of dials, one labeled B0 and one labeled B1. By fine-tuning these dials, you will be able to create all possible lines on a graph. If you were to dial up B0, then the line will shift up. And conversely, if you were to dial it down, it will shift down. Instead, you were to dial up B1, then the line would tilt to a steeper slope. Conversely, if you were to dial B1 down, the line would become flatter before then changing direction and becoming increasingly steeper from the negative side. There is only one combination of intercept and slope that minimizes the distance between the line and the dots. We call it the line of best fit. As for what constitutes the best fit, let's first define the residual, which is the difference between the y-coordinate of an observation and the corresponding y-hat coordinate on the regression line. Such residual will be positive if the data point lies above the line, it will be 0 if it is right on top of the line, and it will be negative if it lies below the line. We define the residual as E equal y minus y hat. The reason why a residual is identified by the letter E is because it comes from the word error, which in this context is synonymous with residual. If you now calculate the square of all the residuals in the dataset so that they all are positive quantities and sum them together, we obtain a quantity that we call the sum of square of the residual, or in short, SSE. There is only one combination of intercept and slope that will minimize SSE, and that is the line of best fit, calculated using the least square method. There is a very apt mechanical analogy for the line of best fit using the least square method. Imagine that you were to build a scatter plot of a dataset consisting of two quantitative variables, x and y, on a wall. Just like a climbing wall at a gym, each pair of x and y coordinates is represented by a peg on the wall. Now, suppose you were to suspend a very rigid but very light hollow plastic pole through a bunch of tiny rubber bands, one for each observation or peg on the wall. One end of the rubber band you will tie to the peg, and the other hand to the plastic pole. Then, you let everything go and let physics equilibrate the final resting position of the plastic pole. Because the potential energy stored in those rubber bands is proportional to the square of the stretch, when you calculate the total potential energy of the system, and neglecting, of course, the potential energy associated to the weight of the hollow plastic pole, the final resting position of the pole will be the one described by the line of best fit using the least square method. Each rubber band would pull back toward its own peg, and the overall energy of the system would be minimized, just as we minimize the sum of square of the residuals. The relationship of intercept and slope of a regression line with the descriptive statistics of the two variables is actually quite simple. The slope, B1, can be calculated as the correlation coefficient R times the standard deviation for the y variable and divided by the standard deviation of the x variable. We can use the Excel formula SDDEV.S to calculate such standard deviation for a simple worksheet of the Butler deliveries dataset, and we have already computed the correlation coefficient R. When we plug in the data, we obtain a slope of 0.069. And what about the units? Remember, when we deal with quantitative variables, the regression equation must equal the left-hand side to the right-hand side in both value and the units. Because on the left-hand side of the equation we have the response variable, the duration of a driving assignment described in hours, then the right-hand side of the equation must also be expressed in hours. If you take a close look at the regression equation, you see that the slope coefficient is multiplied by the distance variable, which is expressed in miles. Therefore, the slope coefficient will have rate units so that it balances both sides of the equation. Those rate units are the units of the response variable over the units of the explanatory variable, or, in our case, hours per mile. Knowing the units of the slope of a regression line is quite important because it allows us to interpret it as the predicted change in the response variable that is associated with a 1 unit increase of the explanatory variable, which in our case translates as observing that there is a predicted increase of 0.069 hours for each additional mile covered on a driving assignment. If you're confused by the units hours per mile, you're not alone. In fact, hours per mile does not make much sense to us. What makes more sense if you were miles per hour, which we know to be a speed. Well, just for this case, what if we take the reciprocal of the slope coefficient? Then it would read as 1 over 0.069 miles per hour, or about 14.5 miles per hour. And what is its interpretation? Well, in this case, this is just the average speed of a driving assignment. Does it seem slow to you? Perhaps you should consider that the truck completing the assignment will have to deal with the city stop-and-go traffic, pausing for snacks, lunch, and rest, and more importantly, stop several times to complete the assigned deliveries. When you put it all together, 15 miles per hour ballpark does not sound that unreasonable after all. We can also calculate the intercept using the mean duration of a driving assignment in hours and mean distance in miles across the whole data set, which we have already computed in the previous video as 70.7 miles and 7.3 hours, respectively. We can now plug those means into the regression equation, as well as the slope, and solve for the intercept B0, obtaining an intercept of 2.39 hours. Remember that the intercept has the same units of the response variable. But what is the interpretation for the intercept? Because the intercept is the y value when x is equal to 0, in our case that translates to the predicted duration of a driving assignment that was 0 miles long. Obviously, that doesn't make any sense. The reason has to do with the extrapolation. See, all 300 observations have driving assignment distances between 40 and 100 miles. And within that range, there is moderate linear relationship between the distance covered by a driving assignment and its duration. However, such empirical relationship is only useful in explaining the relationship between the variables within the range of the data. In fact, we have no clue on whether such relationship would remain linear for values outside the ones contained in our data. Because the intercept is stated at x equals 0, and because there are no driving assignments shorter than 40 miles, that is too severe an extrapolation 40 down to 0 miles to expect the model to remain true to its implied linearity. Nevertheless, such intercept works great to balance the model within the range of the data. We can now write our first linear model for a Butler deliveries dataset. The predicted duration of a driving assignment in hours is equal to 2.39 hours plus 0.069 hours per mile times the distance of a driving assignment in miles. Let's now create a third variable in column C, and let's label it predicted duration. If you now write the regression equation with absolute reference to slope and intercept, and relative reference to duration and distance for each row, we can fill all the cells from C2 to C301. These values are the model's prediction for each observation, each driving assignment in the dataset. Let's also create the fourth variable in column D, labeling it residuals. Let's fill each cell from D2 to D301 as the difference between the response variable in column B and the predicted response variable in column C. As you can see, most of those residuals are quite small, but not all of them. That is because some data points are hugging very close to the regression line, while others just not so much. However, to have a better idea of how the overall pattern of residuals look like, we should build another scatter plot with, again, the distance on the horizontal axis, but this time the residuals on the vertical axis. To do that in Excel, select all rows in column A from A1 to A301 and all rows in column D from D1 to D301. Then, build another scatter plot just as we did last video when we plotted duration versus distance. You can replace the stock title with the Butler Deliveries, Driving Assignments, Plot of Residuals, and add X and Y axis labels as a distance in miles on the X-axis and residual in hours on the Y-axis. Because we have subtracted the contribution by the linear model from the response variable when we calculated the residuals, if the assumption of linearity we made earlier is valid, then the plot of residuals should look like a horizontal band of random dots, like flies on a windshield. In fact, if you calculate the correlation coefficient between the distance of a driving assignment column and the residual column, you will get 0, or no correlation at all. If you don't, it means you may have done something wrong and you should check your calculations. The residuals also have mean of 0 and a standard error given by the square root of the ratio of the sum of squares of the residuals, SSE, divided by the degrees of freedom, which is n minus 2. And why it is n minus 2 degrees of freedom rather than n minus 1? Well, we have a sample of n data points, but we already used up equations to calculate slope and n-intercept, so that leaves minus 2 degrees of freedom. When we calculate the standard error of the residuals for the Butler Deliveries example, we obtain 1.38 hours, which is an estimate of the dispersion of the residuals around the regression line. Another useful diagnostic is the R-square, also called the coefficient of determination in some textbooks. The R-square owes its name to the fact that it can be calculated as the square of the correlation coefficient, or 0.49 in the Butler Deliveries example. Because it is the square of the correlation coefficient, it will always be between 0 and 1, and it will approach 1 as the strength of the linear relationship between x and y increases. However, it has deeper implication with the regression model. If we did not have any information on the explanatory variable distance of a driving assignment, then all we could really do to predict the duration of a driving assignment would be to just take the average duration in the data set, or as we saw before, 7.3 hours, and call it a day. In this incredibly naive model, each prediction of the duration of a driving assignment will always be 7.3 hours. Obviously, that would not be a very precise model. But how imprecise would it be? Well, let's calculate a new set of residuals, and let's call them E sub-index t to distinguish them from the previous ones, defined as the observed duration of a driving assignment minus the mean duration of 7.3 hours. If you now add the squares of all the 300 E sub-index t residuals, we obtain another quantity called the total sum of square, or SST. The reduction in total error from SST to SSE is the sum of squares explained by the regression, or SSR. So it stands to reason that the greater SSR with respect to initial SST, the more the regression model is able to explain the dispersion of the response variable. In fact, if you divide SSR by SST, we obtain 0.49, which is the R-square. The R-square is very important as it represents the fraction of variation of the response variable that can be explained by the explanatory variable. Or, in our example, we can say that about 49% of the variation in the duration of a driving assignment can be explained by the distance covered. These are the foundations of regression analysis. However, we do not have to do all the calculations by hand, because regression is one of the tools included in the data analysis tool pack. In fact, to perform a linear regression analysis using the data analysis regression tool, you should include the ranges for the response and explanatory variables in the corresponding inputs for the y and x-axis, respectively. Make sure to enter the ranges starting from row 1 and select the checkbox for labels. Because our worksheet is already a little crowded, let's keep the default option of displaying the output in a new worksheet. Finally, let's check the boxes for residuals, residual plots, and line fit plots. Select OK. The summary output for the linear regression consists of 3 tables: the regression statistics, ANOVA, and the coefficients table. Let's examine them more in detail. The regression statistics contain the R-square, the standard error of the residuals, and the number of observations as seen earlier. ANOVA stands for Analysis of Variance. It is an important statistical analysis which, however, is not described in this course. However, it is important to point out that the ANOVA table contains 3 rows: regression, residuals, and total. The column DF shows the degrees of freedom. We have 1 degree of freedom for regression, corresponding to the single explanatory variable used in our simple linear regression model. The degrees of freedom for the residuals are 298 because, as shown earlier, it is equal to the 300 observation minus 2 for slope and intercept. The SS column carries all the sums of square, respectively, for regression, residuals, and total. These are the same numbers we computed earlier, which we used to compute the R-square. The next column, we have the mean squares, which are the sums of squares divided by the corresponding degrees of freedom. For example, if you take the square root of the mean squares of residuals, MSE, we obtain the standard error of the residuals. Finally, the coefficients table shows the value of intercept and slope in the first of the numerical columns. The regression output we selected also includes the additional columns for predictions and residuals, as well as the line fit plot and the plot of residuals.